Thank you in advance.
There we go.
All right, here we go. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, August 23, 2024. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a clear and pleasant August evening in my hometown of Rockport, Massachusetts. These Earth and Space Reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining biosphere, and who wonder about the greater cosmos and all that it has fostered throughout space and time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, sundry Earth and space scientists, educators, and communicators, far-flung friends, family, and other curious folk. Thank you for your active participation and encouragements. This evening, we will be introduced to marvelous new images of the nearby star-forming galaxy M51, obtained with the James Webb Space Telescope. Our rock-on tour is Tony Weinbeck, a PhD student at the University of Wyoming. Tony earned his bachelor's degree at MIT and his master's degree at Tufts University. While at Tufts, he worked with yours truly, researching the infrared emission from star-forming activity in the Triangulum galaxy as imaged by the Spitzer Space Telescope. For the past decade, he taught astronomy at Normandale Community College in the Twin Cities while honing his skills in astrophotography. Recently, he has been pursuing extrAgalactic research with the FANGS team, using data from the James Webb Space Telescope. For this evening, Tony will present a feast on the M51 Treasury, a deep dive into the Whirlpool with JWST. In case you were wondering, the FEAST acronym refers to Feedback in Emerging Extragalactic Star Clusters, an ongoing survey of nearby galaxies being carried out by the amazing Webb Space Telescope. This will be Tony's second contribution to these Earth and Space Reports, so welcome again, Tony. The Zoom platform is all yours.
Thank you very much, Bill. So yeah, as Bill said, I am currently working on my PhD at in Wyoming, and I had previously Bill taught me the ropes with Spitzer, so I'm just we're just going a factor of 8 better or so in resolution and depth and everything. So let me go ahead and share the screen. Let's see. All right, just confirming that you can all see the screen here.
Yes.
Great. Okay. So, as Bill mentioned, I'm going to basically talk about, I'm going to spend about the first half or maybe even 2/3 just kind of discussing what the James Webb Space Telescope is, what it does, what it sees, some nuances of it, and then I'm going to get into precisely how we're using that right now to probe the Whirlpool Galaxy, otherwise known as M51. So before I go, I just want to mention. Let's see. One moment here. There we go. Okay. I want to mention some of my collaborators here. So I'm kind of working right now with 3 different groups. The first one, which is the space is primarily on, is the M51 or the JWST Whirlpool Galaxy Treasury project. The PIs are Karen Sandstrom and my PhD advisor, Danny Dale from Wyoming. This is also in collaboration with the FEAST team, as you just mentioned, the acronym. And this is led by Angela Adamo from Stockholm, University of Stockholm, Sweden. And then my other kind of semi-full-time gig is with the FANGS group, which that stands for Physics at High Angular Resolution for Nearby Galaxies. Don't ask how we got the letters, but it's a cool acronym. So with the FANGS group, we have now, specifically with the FANGS JWST team, we have, we're up to 75 galaxies now that we've observed with the James Webb, and we still have a few dozen more to go. So I think the technical terms, I am swimming in data right now, and it is awesome. So the other thing I should mention here is that when I was, so I'm back in Minnesota here, and just prior to flying out here, we're actually we're switching offices at Wyoming, and my computer, I I moved it from one office to the other, but it's not currently unplugged. So unfortunately, I don't have the most cutting edge, the most recent images that we've worked on, but I think there's plenty of images to go around. So unfortunately, though, you won't be able to see precisely what I've been working on for the last few weeks. So I think I might need to sign up for a third talk here, Bill.
Oh, perfect.
So anyway, there's like I said, I think strange. Okay, there we go. This is basically what I want to talk about. Like I said, I want to spend roughly about the first 2/3 or so talking, just giving some background about the James Webb. I do want to go into precisely how the imaging and also the spectral, the spectroscopy works with the James Webb. So there's a total of 4 different scientific instruments. And the cool thing about our M51 Treasury project is that we are using all 4 of those separate instruments to basically do the deepest dive into the whirlpool that anyone has yet done. So I'm going to give some of the background on JW. I'm going to, if we have time, I'm going to show very briefly how we actually go about making the proposals. And I'll show you precisely what the information that what we had proposed, which ultimately was successful. I mean, that's why we have the data here. And then, again, time dependent, I will discuss some future work, which there is a lot more to be done, which is great because that means I have a job for the next few years. So let's get into it. The James Webb, as we all know, hopefully, as we all know, this is NASA's, it's their newest next generation observatory. It looks at specifically the infrared wavelengths. The diameter of the main mirror assembly is 6.4 meters, which is roughly about 21 feet. So it's about the size of a tennis court is what I've heard, or at least half of the tennis court. Another view here in the clean room. So just to see some perspective on it. And this is when it was fully opened up. As you may be aware, and I think as Scott Acton had previously talked about in the series, the actual launching into space, we had to fold it all up, launch into space, and then gradually over the course of about 6 months, open every single mirror, get everything in alignment. And there was something like 250 individual single points of failure that we're able to overcome. But it's a marvel of engineering. And it is to date the most advanced telescope that mankind has ever made. So I am just absolutely lucky to be able to have access to this. Quick comparison between this and the Hubble telescope. So the biggest thing is the Hubble telescope, as you probably know, it looks in the optical wavelengths primarily, so the type of light that our eyes can see. The Hubble actually does, it's still in operation here. It does have a limited field of view in the near ultraviolet and also in the near infrared. So there is a little bit of overlap between that and the James Webb. But the James Webb is almost exclusively infrared, the near and then the mid infrared. And as you can see, it is substantially larger, but also substantially lighter. And the nominal lifetime is 10 years, although the NASA engineers had so precisely maneuvered it into position that it's very likely we're going to have plenty of fuel left over for much longer than a 10-year lifetime here. Also, notice the operating temperature. It's unlike Hubble, the James Webb, and I'll show a quick animation here in a moment, but unlike Hubble, the James Webb has been placed way, way far away from Earth. So it is not actually orbiting Earth like the Hubble does. And part of that is so that we can put it on the far Earth side away from the sun, so that we constantly have a sun shield, as you can see let's see, I think, actually, here we go. We have a sunshade here that blocks the sun from ever contacting any of the electrical elements here. So we're able to keep it at roughly about 40 Kelvin above absolute zero, which is just, it's phenomenal. And so the electronics are operating at extremely cold temperatures. There is extremely little noise is the purpose of that. So again, here is the general assembly of this. The most important 2 things I would say, there's a series of sun shields. So each one blocks successively more sunlight. And the whole point is to avoid any sort of heat and stray light from ever contacting the actual telescope assembly here. And then in the act of when we're actually imaging, so pretty clearly the sun shield has to be perpendicular to the sun, otherwise it's not very effective. So the sun comes here, it hits the sun would be on the bottom here. So the sun would hit the sun shield, and then the telescope up here, it's facing perpendicular to the sun. And there's only a 5-degree wiggle room. So you only can ever move it 5 degrees towards or away from the sun just to ensure that it always stays in the shadow. And that I'll come back to why this is important here later in the talk. But because there's only really about a 5 degree roll in that axis, there's a very limited window for observing any given galaxy, depending on the location of it in space. So, for example, with our galaxy, we only had about a 3 week window to observe it because that angle that's looking at towards M51 was so relatively small that if we miss observations, you literally have to wait until either 6 months later or a full year later to regain those observations. So I'm kind of foreshadowing here. But like I said, the James Webb Telescope is not actually in orbit around the Earth. It's at what we call the L2 Lagrangian point, which I have a short video here that probably explains it better than I could. I'm going to skip through. I'm going to play about the first 2.5, 3 minutes of this here.
After a 1.5 million kilometer journey, the James Webb Space Telescope has arrived at the Sun-Earth L2 point. It did this by executing its final mid-course correction burn called MCC2. It lasted just 297 seconds, or a little less than 5 minutes, and it only changed Webb's speed by about 1.5 meters per second. That's a brisk walking pace. It may not seem like much, but it was enough to place Webb into an orbit around L2. In fact, it placed it into a very large orbit, one that's more than twice as large as the moon's orbit around Earth. It'll take Webb about 6 months to complete a single orbit around L2, and this first go-around is jam-packed with mirror alignments, phasing, instrument calibrations, moving target tracking tests, verifications, station-keeping maneuvers, and finally, the first science observations. But what exactly is so special about L2? I mean, it's just a point in space, and it's an empty point in space at that. So how can Webb orbit something that isn't there? Well, it is true that L2 is empty, but orbiting empty points in space is actually very common. And that's because whenever there are two massive bodies that are orbiting each other, they both orbit a common center of mass, or barycenter. If the objects are massive enough, the center of mass lies somewhere in between. We only say that the moon orbits Earth because its center of mass is located inside Earth. But Pluto and Charon have similar masses, so their barycenter is somewhere in the space between them. So the fact that something can orbit an empty point in space really isn't all that unusual. But at the same time, that's a two-body system. It doesn't explain how Webb can orbit a point that's outside of another two-body system. Well, the good news is that
forward just a tad.
L2 is one of the 5 Lagrangian points between the Sun and Earth. Actually, these 5 points exist around any two-body system. So there are Lagrangian points for the Earth-Moon system, a set of points for the Sun-Jupiter system, and so on. Now, if a third object is placed at any of these points, the gravitational forces of the two large bodies combine in such a way that holds the third object stable with respect to the others. The practical upshot is that as the system orbits, the third body tags along. And that's why the Sun-Earth L1 point is a great place to position sun-facing missions like the Solar Heliospheric Observatory and Earth-facing missions like DISCOVER. Likewise, L2 is the place to put astrophysics missions like Gaia and Webb. At both locations, spacecraft maintain a constant line-of-sight communication with Earth, even as Earth orbits the Sun. But L2 is particularly important for Webb because it can block the heat of the Sun, Earth, and Moon with a single sun shield. That's a perfect place for infrared astronomy. But there are some important caveats. For one thing, the third object has to have a mass that's really, really, really small relative to the larger bodies. Now, obviously, that's not a problem. Webb's mass is negligible compared to Earth, let alone the Sun. But the other caveat is that the Lagrangian points are at best described as metastable, especially the first 3 points. To understand what I mean, imagine a saddle that's perfectly smooth and frictionless. Now imagine trying to balance a marble in the very center of the saddle. It's theoretically possible, but as a practical matter, it's extremely hard to do. The L2 point is a lot like this. An object moving perpendicular to the Sun-Earth line falls toward the center, but then it either falls toward or away from Earth. Now, if Webb falls away from Earth, it's really in trouble because the only way to bring it back would be to turn it around and thrust back. But that would cause the telescope to suddenly warm up, all of the structures would expand, glues and adhesives would melt, and the mission would be over. And that's bad. Webb has thrusters only on the warm, sun-facing side of the observatory. And that's because hot thrusters would contaminate the cold telescope side with heat or with rocket exhaust that would otherwise condense on the optics. That would also be bad. A safer approach is to place Webb almost, but not quite at L2. And that way, when it falls back toward Earth, a tiny thruster burn pushes it back almost, but not quite back to L2. And this means Webb never runs the risk of actually falling beyond L2 where it cannot be recovered. And that's why the Ariane 5 launch was intentionally designed to slightly undershoot and let the spacecraft do a series of mid-course correction burns.
So I'm going to pause it here. The one other thing I wanted to point out, if you probably saw in this diagram here, I'll play it briefly again. Notice that it's actually in kind of a up-down orbit.
It may not seem like much, but it was enough to place Webb into an orbit around L2. In fact, it placed it into a very large orbit, one that's more than twice as large as the moon's orbit around Earth.
Right here.
It'll take Webb
not sure if it's obvious, but
6 months to complete.
But there's a very good reason why we don't just put it right at that dot. So in other words, we have it rotating around that Sun-Earth line instead of around that versus directly behind it. And the good reason for that is that the James Webb Telescope is solar powered. So if we put it in Earth's shadow, we're not getting any solar power at all. So that's why we have a kind of orbit around that semi-stable point, and it will always pull back towards the center in that plane. But like you said, it does tend to fall towards Earth. So we just gently thrust it every once in a while, and pretty clearly we only use those thrusters when it's not actually taking images. So, let's see. So, like we said, it orbits at the L2 point, and it has that sun shield constantly blocking any sunlight and any stray heat so that it can, in fact, do infrared astronomy. All right, so let's talk about specifically some of the science instruments on the James Webb. And as I mentioned, there are 4 distinct science instruments. Each of them has a different purpose, and they look at, for example, different types of light. They do different tasks. So we're going to go through 3 of the 4 of these, NIRCam, MIRI, and NIRSpec. I will mention that the fine guiding system and NIRISS, we don't actually employ that in our observations. However, the MIRI instrument has 2 separate modes. We have the imaging mode and then the spectroscopy mode, and we almost view those as two separate instruments in itself. So we do have that guy, that guy, that guy, and that guy. So that's why I'm saying we're using all 4, even though it's not exactly this thing. So let's go through each of these a little bit, and I want to talk about exactly what wavelengths we look at, what some of the nuances for each of these instruments here. Having issues with my pointer, I apologize. Come on, there we go. Okay. So the cool thing is that all 4 of these can, in theory, they can be used simultaneously. Now, in reality, we don't typically use all 4 of them at the same time, but they're all located along the focal plane. There's an extremely complicated series of anywhere, depending on the instrument, anywhere from about 5 to 8 different mirrors and lenses, guiding systems to focus a light onto different areas within the telescope. But the general layout of each of these, here are the NIRCam detectors, here is the MIRI detector, here is the NIRISS spectrometer and the NIRSpec spectrometer. This is actually their direct field of view. So you could literally, like, if you're looking at M51, you could imagine the whole galaxy behind this. Each of these sees a slightly different part of the galaxy. And so right here, so for example, if we're looking at, like, this is all one continuous image, and we're seeing little windows of that image for each of these different elements. So you can't ever take exactly the same field of view with MIRI and NIRCam at the same time. So one of the things that we have to do is if we want to image the same area, you take some images with NIRCam, then you shift it slightly, you roll the telescope so that the MIRI detector is now in the same location as the NIRCam, and then you take your images with MIRI as well. Let's see. It is interesting that they're all perfectly placed along the focal plane, and there's very little, but there's a slight amount of distortion, but very little distortion between all of the elements here. First of all, this is looking at the NIRCam, and I had to show this because you might recognize this guy right here. This is actually from Hubble imagery, but this is actually a photo of the Whirlpool Galaxy, and you can see why we call it the Whirlpool Galaxy. This is the main M51, or you can call it, the other name for this is NGC 5194. This galaxy is actually NGC 5194A. This guy right here is NGC 5194B. And what's actually happening here is that this dwarf galaxy is literally being sucked into the main big spectacular spiral galaxy here. And if we had a few more billion years to live, we could actually see that this guy eventually will kind of stream in and they will coalesce into one larger galaxy. So the other thing to point out with this is that this is the wavelengths, at least the visible to longer wavelength part of the electromagnetic spectrum. The field of view for NIRCam, it's called NIRCam because it's near to the visible part of the spectrum. So we have just a little bit of coverage in the visible range. So we can see some very red wavelengths that our eyes can see. But the rest of the coverage for NIRCam is in the shorter wavelength infrared. And this field of view, you see there's actually two separate fields of view. That's because there's two independent detectors. And you can see that, right here, there's two separate detectors. We call this module A and module B. And they see slightly different fields of view. And this is literally to scale for exactly how much of the galaxy we can view at one time. So what this means is that in order to actually image this entire galaxy, you would need to do a series of exposures from, for example, left to right, shift it down a little bit to fill in this gap, left to right, maybe do it again to get the outskirts. What we've actually done is we've taken kind of just a vertical strip. So it's not actually in the same layout, but we've taken a vertical strip that extends from about right there to right here. And you'll see this here momentarily. It's not because we're not interested in the other stuff, but it's able to give us a more likely proposal to be accepted if we're not asking for 80 hours, we're only asking for 20 hours, for example, of telescope time. So this is actually the NIRCam, one of the two NIRCam detectors. It's either module A or module B, I don't know. But you can see physically how large that is. Now, the detector in a typical consumer grade camera or a DSLR is about a quarter of the size of one of these four sub-detector arrays here. So this whole thing it's gigantic compared with normal detectors. And that's for a couple of reasons, but one of them is that we get extremely high sensitivity, and also we're maximizing our field of view with this camera here. Put all together, this is what the entire arrangement just for the NIRCam camera is. So like I said, there's anywhere from 5 to 8 or so individual optical elements. The one thing that I want to point out, a couple things here. This is the incoming light from the main mirror on the telescope. So that big, giant 21-foot mirror, the light strikes it, it hits this what we're calling the pickoff mirror, and then now that will reflect it towards this guy. This guy reflects it, or this guy passes through this thing here, and then this dichroic beam splitter. This is really key for the functioning of NIRCam. So the colors here are quite intentional. We see the blue light, when it hits that, the blue light reflects off, and blue is indicating the shorter wavelength. So the wavelengths that are slightly visible to about a little bit into the infrared spectrum. So the shorter wavelengths bounce off this, whereas the longer wavelengths will actually pass right through that. So that's why it's called dichroic, or two-color splitter. So we're actually able to image two different wavelengths at the same time, which is spectacular. So we literally can split our observing time in half. If we want to take an image at, say, 2 microns and 4 microns, we can do that simultaneously. So our observations in M51 absolutely take advantage of this. So every exposure we take is actually using two separate wavelengths. And then there's a whole series of bouncing back and forths and detecting stuff. But this dichroic beam splitter is super important for the functionality of the James Webb. And this is what this actually looks like physically. So you see, again, just how large this thing is. And I would venture to guess this is probably the single most expensive camera that has ever been made. So we have to be extremely precise with these, with the optical elements and the electronics here. So that's NIRCam. And then we're going to come back to this here shortly, but I just wanted to show there's a whole series of individual filters, and I'm going to skip forward just momentarily. There's actually a total of 4 separate filter wheels, and I'm kind of including the pupil wheel. I'm not going to get into the technicals of this, but we see there's a whole, there's what is this? Each of these has, I think, 6 individual options, 3, 6, 9, 11. Okay, 11 times 11 times 11 times 11. So whatever 11 to the 4th is, there's that many different arrangements that we can use for any individual exposure. So there's a huge range of possibilities depending on what science you're trying to do. And again, you can use completely different arrangements for the pupil wheel, the filter wheel, the long in the short wavelength and the long wavelength channel here. But again, this is the, let's see, I'm going to flip to the chat here. So this is the filters. And like I say, I'll come back to this, but the whole point is that this is a cutoff between the short wavelength channel and the long. And there's everything from an extremely wide band where we're basically just capturing all the light regardless of wavelength for the short and the long channels. And then we get to the wide filters where they're actually somewhat narrower. So these will encapsulate a fairly wide range, which it's similar to, for example, like the VBRI Johnson filters that astronomers tend to use. Then we get into the medium range filters, which this will actually focus in on a smaller range of light. And then we have these extremely precise narrowband filters. And these are used for a really important purpose, and I'll come back to this later here in the talk. So again, the whole point is that NIRCam has a fairly wide range of wavelengths, and it has a huge versatility for what we're trying to do. Okay. So again, this is the field of view for NIRCam. Now, just to compare, here is MIRI. So again, MIRI, notice that we have slightly longer wavelengths. That's what the M in MIRI, it's mid-infrared versus near infrared. So notice a couple things. First of all, we have a smaller field of view for MIRI. There's a reason why it's kind of slightly rectangular shaped. There's actually a little bit of an extra part of the detector here, but it tends not to come up. It's used for purposes typically for looking at stars and whatnot versus like wide angle surveys. So not only is it a smaller field of view, but also notice that it's slightly tilted relative to these detectors. And this is another bit of a nuance that we have to take into account when we're making our proposals. You can never quite get exactly the same field of view from MIRI and NIRCam, even after you pan over. So a little more detail on MIRI here. This is, I think it's just a beautiful image. This is the filter wheel for MIRI. And just like for NIRCam, you can choose different filters to focus in on different wavelengths. And there's a few other things here. You can see that some of these filters have a weird little pattern. These are used, they're called what we call coronagraphs. And basically what we can do is, I'll take this one for example here, we can block out the light for a main central star. For example, if we're trying to look at a very dim planet just next to a very bright star, the only way we would really have a chance to do that is by blocking out the light from the star and hoping to see the planet right next to it. So some of these, this guy, are all, these are all coronagraph filters, whereas the rest are the light filters, the standard ones. And similarly, here's the range of filters that we have for MIRI. So we see here, and oh, by the way, I should talk about exactly what the numbers mean. So the easy way to do it, you divide the number, let's say 560, you divide it by 100, and that gives you the wavelength in microns. I'm gonna go back to the NIRCam one here. Again, for all of these, you divide that number by 100. So for example, the 150 filter, you're seeing 1.5 micron wavelength light. Now, as some of you may know, the visible part of the spectrum, so here we would see 0.7 micron, or we say 700 nanometer light. This is that one filter that does fall in the visible range. So at 0.7 microns, we're still in the visible part of the spectrum. After that, at 900 nanometers or 0.9 microns, this is where really the infrared truly starts. So again, just you divide that number by 100, and that's where you get the wavelength in microns. And microns is the typical like currency in infrared wavelengths. So these filters, again, there's a somewhat of a range, but essentially we're spanning all the wavelengths from about 5 microns up to about 25, roughly 30 microns, which at that point we start getting into what we call the far infrared, and that's where the Webb stops. So finally, just very quickly here, near spec, this is one of the 2 spectrographs. And again, just as a quick review, the difference between imaging, we're taking essentially a photo of the galaxy. We're looking at how much light from each different like spatial portion of it. Versus spectroscopy, what we're doing here is, I'm going to bring up an image and I'll come back in a second, but instead of looking at a photo of it, what we're doing is we're looking at a very specific region, and we're seeing exactly how much light we're getting at each individual wavelength. And near spec and also the mid-infrared spectrometer, this encapsulates both of them. They're built to be extremely sensitive, so we can get extremely precise wavelengths. And what that allows us to do is to look at exactly what, for example, what chemical elements are in a given part of a galaxy we're looking at. So again, spectral imaging, we're looking at what wavelengths of light there are, and specifically what chemicals there are, versus imaging, we're looking at pictures. So one example of where near spec is where we've used that, this is a colleague of mine, Ryan Chowan, from Ohio State, and then the whole list of authors is something like about 80 or so. Ryan told me this is one of the most difficult papers he's ever written, because half the authors are chemists, half the authors are physicists, and everyone wanted something different in the paper. So it was kind of a game of politics writing this. But this is an incredible paper here. And what he's done is he's taken, I'm going to move down here. He's taken, focused in a single region in the bar of the Orion Nebula. So anyone who's done astrophotography almost certainly has imaged the Orion Nebula. There's kind of a big C shape that goes right here. And it's one of the coolest things in the sky. But so he has zoomed in very precisely into this bar of the Orion Nebula, and he's focused in and taken very precise spectra of different physical regions. And so what he can do is look at what are the different, like what are the elements, and then, for example, like how excited or how energetic is each of these regions. We can tell that from the spectra as well. So precisely, he's looking at what we call an H2 region. That's, when we say H2, what we mean is a very hot region of hydrogen gas, or specifically ionized hydrogen gas there. The atomic PDR, what that means is photo dissociation region. So there are atoms here, but because of the nearby, the trapezium, is it the trapezium?
Yes.
Bill? Yes, okay. The trapezium, the 4 stars in the center of the Orion Nebula, the 4 very hot young stars, are photo dissociating, or it's literally destroying the atoms here. And we're looking at exactly what the spectra of this region here looks like. And then we have the DF means dissociation fronts. So there's basically shock waves, and you can kind of see those shock waves being traced there. And the cool thing is this paper, by the way, if you're interested, it's just a tour de force of what we can learn using just simply spectra from the Webb. But some of these dissociation regions, we can learn a whole lot just by focusing on exactly what the spectra look like. And the really cool thing about this is that we can identify, this is a very standard spectrum for some of these hot ionized regions, or dusty regions in galaxies. And the cool thing is, for each of these spikes here, we can identify exactly what type of molecules or what type of molecular dynamics are causing each individual spike of wavelengths. And to go a little bit further, what we now understand, this is from a talk by Brett McGuire, who's now a professor at MIT, and honestly one of the best speakers I've ever seen. When I saw him speak at the AAS conference last winter, he has just some amazing animations of, if you vibrate them this way, it will cause, for example, this wavelength. If you vibrate them this way, it'll cause this wavelength here. And so what we're doing is we're seeing these big rings these are mainly what we call benzene rings, or big carbon rings. They're organic molecules by definition. And depending on how they stretch or how they vibrate, they give off different wavelengths of light. And each different size molecule will give off a slightly different signature of light based on how it's vibrating. So the cool thing is he has now identified something like 250 molecules of these different benzene rings, depending on how many atoms they have. So these aren't quite rings here. 2 and 3 can't make a ring. But all of these here on are what we call polycyclic aromatic hydrocarbons. Try saying that fast. Polycyclic aromatic hydrocarbons, or PAHs. PAHs is what we call them, or what I call them. There is some disagreement with the astronomy community. Some people adamantly say you have to say PAHs. I think that's BS. I just say pause. Anyway, we can literally tell based on the spectrum of the light that we're seeing exactly what organic molecule we're finding in space. And again, the point is that we absolutely do see these organic molecules. And that's obviously important because if we're actually looking at molecules in space, we're seeing organic molecules. That is, in fact, the precursor of life. So I don't want to spend too much on that, but the point is, though, that using the spectral portions of the Webb, we can in fact look at the chemistry in outer space. And then the last thing I'll mention here, just very quickly, if we look at this peak here, some of these the PAH molecules happen at 3.3 microns. If we look at the NIRCam filters, hey, there is again, divided by 100, a 3.3 micron filter. We look here, there is a feature at 7.7 microns. Hey, there is a 7.7 micron filter. There's a feature at 11.3 microns. There is an 11.13 micron filter. Oops. And so literally the filters that we're using for the Webb have been designed very specifically to look at exactly these types of peaks in the spectrum, because this is precisely the wavelengths that we know that these organic molecules will be glowing in. So there was a very intentional distribution of these different filters because we specifically knew that we wanted to investigate these organic molecules, these PAHs in space. So moving on a little bit. So actually to M51, which is kind of the heart of the talk here, just as a bit of a background. So this is an image from 2005, and it was, I mean, Hubble had been up for 15 years, but still, it was one of the most incredible photos that the Hubble ever took. And the cool thing about this image here was that going from the bottom right to the top left, these are literally the raw observations that the Hubble took, the unprocessed, the uncalibrated images. And then the gradient going up to the top left, these are the fully processed, the fully calibrated data. So we see basically what the data looks like going from raw to not at all raw. Zooming in a little bit there, this is the final image here. And I just think this is beautiful. Again, M51A and M51B there. The red, the super red little pockets here, this is what we call the H2 regions, or these hydrogen regions. And there's an analog in the James Webb that we're seeing at slightly longer wavelengths that I'll get into in a moment as well. So this kind of setting the stage what Hubble had looked at, and now the James Webb, we were really the first two. The FEAST group was the first one to see what this looks like in infrared, and that's what this looks like here. So the FEAST collaborations group, it made big headlines. It was from, let's see, okay. I was just floored when I saw this. And like I said, we're just looking at a single stripe across the galaxy. They only took 4 wavelengths. I'm sorry. I think they had 6 individual filters they used. And this is a combination of all 6 of them for the longer wavelengths in red, the shorter wavelengths in blue. That's pretty typical in astronomy. So the FEAST group, it stands for, again, Feedback in Emerging Extragalactic Star Clusters. This was kind of the proof of concept that, hey, we can see a whole lot more with the Webb than we could even with Hubble here. So what we did as a group, this is our proposal for that was led by my advisor Danny Dale and by Karen Sandstrom. No need to read all of this, but basically what we're saying is that there's a whole lot of stuff that we can learn from M51. Let's take advantage of not only how near to us it is and how edge on to us, but let's also use all the rest of the filters that FEAST didn't get. And this is what we end up with seeing here. So between combining the FEAST imagery and the M51 observations, we have 24 separate filters now in viewing this, which is, to my knowledge, the deepest we've ever seen, or the broadest, I guess I should say, we've ever seen for any galaxy, at least in the infrared. And right now, I literally have all of that data on my computer. only about maybe 30 people in the world have ever seen it, and we're really trying to process and chomp through it so we can actually publish this. It actually is in the public domain, so you could actually go into the James Webb, we call it the MAST archive, is what we say, and you can literally download all of this data right now. It's all in the public domain. We want to be the first ones to publish this, so we don't want to get beaten to the point. But notice that there's a combination for the W indicates the wider bands, the N indicates the very narrow bands, and then we literally have all but one of the Miri bands. We have all but the very longest Miri band. So there's some amazing science that we can do with this, which we're only just hitting the surface right now. In the first, we've had this since we got the observations in June, and so we've had it for about just over 2 months, and we're just now starting to write the first papers. So there's stay tuned to this. I want to show you what this looks like though. So again, we have 24 bands. So going from slightly over 1 wavelength, what we're seeing here, and I'm going to zoom in. Ooh, I'm going to zoom in here. This is almost entirely just stars, stellar continuum. We're seeing a combination of red stars and fairly hot, fairly bright blue stars. And we see very clearly there is just this huge density towards the center. The center of M51 is just incredible. And then the spiral structure, we are seeing these dark patches here. And those dark patches aren't, at least these dark patches here and like there, this doesn't mean an absence of stars. What this means is there's dust. And the shorter the wavelengths, the more the dust obscures the light behind it. So when we're looking at the wavelengths very near to the visible, this is almost visible light, we are seeing dust obscuration, just like the Hubble saw. But then going towards longer and longer wavelengths, we're seeing there's still at 1.4 microns, there's still some of that obscuration, but less of the extinction. Here's 150, we're seeing less and less of that dust there. And then, let's see. Okay, so we're going to come back to this in a while, but notice that there are clearly missing patches. Like I said, I'll come back to that. But remember, like I'd said, our field of view is not nearly as wide as the whole galaxy. So what's essentially happened here is that we've tried to kind of pan across the whole way. And during the observations, we were trying to span these gaps, the observations failed. So if I have time, I'll come back to discuss about how we're going to deal with that. So anyway, this is what we call the NIRCam short wavelength filters. And as we go further and further, we're all of a sudden starting to see that there's essentially no dust obscuration at all. And we're starting to see what looks like more kind of spread out sources versus point sources. So we're starting to see more and more contributions from dust and not just individual stars. And by the way, one other thing, I guess I'm even glossing over this. We are literally seeing, I guess I can't go further, but we are literally seeing individual stars in a galaxy that's millions of light years away. And that still just floors me, that we can literally see individual stars in other galaxies. So we have sorry about this. We have the shorter wavelength NIRCam. We have the longer wavelength NIRCam. And again, a number of these filters have these gaps because we lost those observations in not just one waveband, but in multiple at the same time. Remember, we can do simultaneous observations. So we have, again, 2.12 microns. Now, the N, remember, these are the really narrow filters. This is looking very precisely at molecular hydrogen. So we're focusing only on light coming from molecular hydrogen and nothing else here. And I will say the same thing down here. This 405, trying to recall precisely. Oh, this is hydrogen. It's called the bracket alpha wavelength. For those of you who are familiar with that, it's a very precise, it's a 4 to 3 transition within the hydrogen atom. If you don't know what that means, don't worry. We're seeing hot hydrogen there. And then even going back to the last page, is not ideal. Here we go. Okay, the last page, we also had 187, and this is another hydrogen transition. This is the Passion alpha transition here. So this is actually what I'm spending the most of my time right now working on. There's a square missing, which is my fault. So moving on just a little bit, we have the longer wavelength NIRCam. And again, each of these looks slightly different, which is cool. That means that we're actually seeing real science here. And then finally, the Miri wavelengths. We have 8 different Miri bands. And again, we're seeing different stuff in each band. So the 7.7 tends to be the prettiest of all the bands. It's I think maybe tied with my first favorite, the 7.7, and then also the 11.3. And I absolutely love this image here. The 11.3 micron band is just incredible. So again, this is tracing the dust in the galaxy. Very precisely, it's tracing these PAHs, the PAHs. And by looking at the dust, we're seeing both gas that has been expelled from stars, so the aftermath of, say, supernovas, but we're also seeing clumps of dust that are actually coalescing into a new generation of stars as well. And so we're literally seeing the life and the death of stars all in one image for each of these different filters. And as we go to longer and longer wavelengths, we're seeing larger and larger dust molecules is one of the differences as well. So we're taking slice by slice. We're seeing very different features and very different physics happening just simply by looking at slightly different wavelengths. This is 21 microns. This is tending to look at just warm gas here. And it's not precisely a certain molecule or anything. So this is where we're at here. We have 24 wavelengths of light in M51. We are midway through processing these. There's a lot of science still to come, a lot of questions that we're answering, a lot of questions that we're now just learning to ask, which is part of the fun of science. And in addition to that, I'm just about finished here, so give me about another 2 minutes. But in addition to that, we also have spectra. Like I said, we're using 4 separate science instruments on the web. So this is an example of the mid-infrared spectrometer. So notice that we're seeing slightly longer wavelengths that correspond with, for example, right around here in the spectrum. So the mid-infrared spectra, if you focus in right in this bright little dot here, we're seeing a very bright 7 micron peak here and about a 6.6 micron. We think that very likely might be what we call deuterated PAHs, or these organic molecules that are made from, instead of hydrogen, deuterium instead. Again, if you're not familiar, don't worry, but we're literally peering into exactly what the elements in this exact region are. This is an example of the near spec data. So the cool thing is, for the same region, we can take what we call a slice. So we focus in at one specific wavelength, and so we can make a picture at any different wavelength, because we're actually getting, for each individual pixel of data, we're dividing the light into all the different wavelengths. And so you can take a slice at exactly a given wavelength and see, for example, this 3.3 micron PAH feature. We can see the distribution of that. Here's what this element, how that's distributed. The aliphatic 3.4 microns is showing a slightly different version of that same molecule. It's slightly differently dispersed. This is the FUND series, PFUND or PFUND, I don't know. And so basically we're looking at, when we take a slice of different wavelengths, again, we're looking at the distribution of different elements in one very precise little small part of the galaxy. So we are doing a deep dive into this. So this is basically the 4 different, we're using all 4 science instruments. We are flush with data, and if you give us about another 3-4 months, these articles are going to start coming left and right. And it's going to be really exciting to see all of this new science that we have, even though it's one of the nearest galaxies to us. So very briefly, I just want to mention we are what I'm specifically doing, and this is why I'm saying that I might need a third talk here, Bill, to kind of fill us in this. But what I'm actually, my day-to-day work right now is I'm trying to process these, what we call the narrowband images. So I'm trying to remove the starlight from these so we can very precisely see only, like, for example, the red dots there. Or maybe we can only look at the molecular hydrogen or the ionized iron. So it's somewhat complicated. We have to work these very differently than the wideband filters. But Elias Oakes and I are working on this. And so stay tuned with that. I've started writing the paper, but we're not quite there. And the other thing that I'm working on, this is basically the last slide here. I am working on essentially combining all of our filters for all of our wavelengths, and also including all of the wavelengths or all of the observations we've taken from the FANGS collaboration, and doing a pixel by pixel by pixel analysis of exactly what the light looks like at all different wavelengths. And the long and the short of it is that my guess is if we can employ machine learning, we can make very strong predictions on, for example, these gaps in the images here. I have a very strong belief that we can actually fill in these gaps by interpolating between the nearby wavelengths here, using machine learning and the knowledge that we already have. And same thing here. These gaps that we're missing, we can use the kind of the surrounding wavelengths and then predict what they should look like, because we have to wait an entire year to get these other observations. And this goes back to that 5-degree range that we have. We miss those observations and we have to wait literally a whole year to actually get the true data. So this is a longer project, and it's very possible this might end up being part of my thesis, but that's what I'm working on right now. And what I will leave you with is our family picture here. This is all the observations put into one. The blue is the NIRCam short, green is NIRCam long, and red is MIRI. And this doesn't even include our spectra data that we have too. But so yeah, that is a deep dive into the Whirlpool Galaxy. And the exciting thing is there's so much more to say that we haven't put the sentences together yet. But that's where we're at. So thank you very much.
Thank you. Awesome. Let's get the gang here. Gallery. All right. Do
Tony,
anybody want to ask a question? I see Bill Wall has a question.
Tony,
Yeah.
stabilizing flap.
Stabilizing flap. I'll pull up the picture here. I'll share the screen in a second. Yeah.
What?
So I think you're discussing this. Let's see.
The flap on the JWST and
Right there, right?
It's a stabilizing flap.
Let's see. This thing right there.
There you go.
Yep. Your guess is as good as mine.
Okay, I thought
I was not involved in engineering.
I wanted to ask.
Bill.
Well, sounds self-explanatory.
I'm wondering if it might have to do with the radiation pressure that's hitting the warm side of the sun shield. I'm not sure about exactly what the function of that is.
Okay.
This is a
It's
great
like
question.
seeing a spoiler from a 56 Buick on a DeLorean. You know, what's that for?
Yeah, it's the is this to keep the downforce on the car when it goes? No. No, I literally have no idea. I wish I could tell you here. I mainly know the things that are inside this little panel right there, and that's really all that I need to know about right now. So
I said I couldn't get past stabilization flap for the whole thing.
Yeah. Yeah, like I say, I don't know. I do know that we have a series of gyroscopes, just like the Hubble does, to make sure that it stays at exactly the precise orientation while we're taking our exposures. I couldn't tell you though.
So Tony, could you stop sharing?
Yep.
Okay. And I'm going to interrupt Artie. Bill Wall, would you like to say something? Ask something?
Yeah. So hello, everyone. And yeah, I really enjoyed your talk. I thought you did an excellent job there. Yeah, I have a couple of questions. One is M51 is not what you'd call a typical spiral galaxy. So in what way is it useful in understanding galaxy evolution, given that it's exceptional in certain ways? For example, the very strong spiral density wave.
So it's a number of things. I mean, first of all, it's one of the nearest to us. So, we have one of the best spatial resolutions for at least any, face-on galaxy. The other is that, so with that, we actually have that diagonal slice leading up towards the M51b. So we actually, at least in the nearby part, we are seeing some of the incoming gas. It's a very active star-forming galaxy, so we are seeing some very bright regions of hydrogen alpha and also passion alpha. These are the hydrogen transitions. I believe it's fairly metal rich, which is why we have the iron 2 wave band. I think Bill Waller, you might know better than I about some more unique characters of M51.
Well, one really neat thing is what Bill Wall noted is that the density waves are are strong with this galaxy.
Yeah.
And
And I'm just wondering how representative it would it be of other galaxies. So you learn something about galaxy evolution from this, and how well does it apply to other galaxies? I mean, do you have some sense of that?
Yeah, that's I wish I could answer better. What I will say is that within the FANGS group, we have, like I said, we have 75 galaxies, and about a dozen of them are some of the Messier classified ones. We have M64, oh geez, can't think off the top of my head, but a number of other of the Messiers, which tend to be the brighter, nearby, more spatially resolved ones. We do see similar spiral structure for many of these. M84, NGC 628. This is one of the most
M74
Webb ones. Yeah, M74. This is one of the most iconic James Webb galaxies. And one of the things with both M74 and M51 shares, there's very strong bubble features that we think are caused by feedback within the galaxy. For example, either strong stellar winds, or in many cases, we think probably recent supernovae that have basically cleared out a region of gas and dust. And actually, my poster at the WS meeting this past February was January was specifically looking at what's happening at the edges of some of these galaxies in one of the other Messiers. And so, because of the spatial resolution of this, we can actually look at exactly what the triggered star formation is right on the edges of the bubbles, which is a really interesting thing.
So cool.
There's and again, there's a lot more science we can do with it, which I wish I was more of an expert in already.
Okay, more to come, in other words.
Yeah.
One final question is about you said you could fill in the gaps in the data, gaps in these images.
Yep. And
my guess is you've already thought of this. It seems like what you can do is you can artificially induce gaps in your data, and then see if the algorithm will actually fill it in properly, right?
That's precisely one of our tests for one of our diagnostics. Can we remove that, train all the data on the entire set of data except for one region and one little filter, and then compare our prediction versus the true data. So this is actually a new and developing field that my new office mate is actually working on a similar thing with some other galaxies. But there was literally a paper that came out earlier this year, essentially doing a proof of concept for this. And that's precisely how, so we can do, this is called the trained, I think that's the word, trained versus untrained machine learning. So this would be a trained machine learning there. So that's kind of our control set.
Right. Okay, thanks.
And yeah, there's combining the 24 James Webb filters, we have 5 extra Hubble, and then even Herschel in the the microwave. We should just be able to really make a very strong case for what those regions should look like without ever knowing it. So,
right. Okay, thanks.
Artie, did you have a question?
Well, yeah, probably, and I've forgotten probably most of it. First, thanks, Tony. That was a great presentation. I think I caught most of it. I guess one of the questions I had was in the very beginning when you were showing the aurora, what energy level are those interactions up in the sky? I mean, how do you calculate that kind of an energy to deliver that?
All I do is I put my camera up and I hit it close. Though I do know there's another expert on this here in the chat room already. So Bill.
Yeah, it's the green and the red are from oxygen, which has been collisionally ionized by and excited by the incoming particles.
Megajoule range?
Oh, I don't know what the actual power is. That's,
I mean, it's got to be something that
energy.
Lighten up the sky. Yeah, it's a pretty sight. I love those.
The particles have to come in at several hundred kilometers per second.
Wow. Okay.
That's why you don't usually get it with just the plain old solar wind. You need a little more oomph.
Yeah, I'm sorry we missed it here because of the smoke or whatever was missing.
Yeah.
So those dancing sprites, are they real or are they resonance that get set up? You said they were moving in unison.
Like the spires.
Yeah.
Yeah, and the cool thing is that they were very visually very bright, like white and bright. And with the camera as well, I was very, very clearly they appear as white overlaying on the the red and the green. I don't know nearly enough other than just what they look like after I hit expose on the camera. I suspect though it's a combination of excitations of different elements in the atmosphere there, or maybe a higher atmosphere. I'm not quite sure.
The other question I had was the exposure time on
Sure.
your JWST exposures. How long do you have to usually operate it to get your image?
Sure. No, that's a great question. So each of our filters, we have over 10 minutes of data. And so combined, 24 individual filters times, anywhere from 10 to 20 minutes, we're looking at a few hours of telescope time. Oh, there we go. Steve's. Yes. So we're looking at numerous hours. And the thing is, for every single observation, there's usually about an hour of like overhead time to, slew it. And then typically about another hour of overhead time, depending on how many filters you're using to change the filter wheels, to do the slight dithers. So overall, we had basically it was for our observations, specifically with the M51 Treasury, we had almost 2 consecutive days of James Webb doing nothing but M51. And that's separate from Feast, which they actually had longer exposures for each of their filters because they only used 4. So yeah, we literally monopolized the web for a couple days in early June. It was pretty awesome. There's actually websites that you can go to and it will tell exactly like show on the sky where it's looking. And it was like, just, I was doing it while I was doing the exposure. And it's, there's M51 and says, like the M51 Treasury project. So
you get the results very quick?
Within about a day. Yeah. And we knew within a couple hours that some of those observations had failed. And so everyone went in panic mode and we did our best to like try to repropose to get those gaps we had about a 2-week span that we could have in theory filled in those gaps, but they didn't give us the telescope time. So we literally have to wait until next year to get them instead.
Great results.
Yeah. It's exciting to be in this position here.
Yeah,
you're glowing.
Well, that's also a bit of a sunburn, probably.
One question: do you capture H alpha at
so that's what the
0.65 microns?
Yep. So that's what the very first filter, the 070 filter is.
I noticed that.
The reason we didn't use it though is that the 2005 HST observations, one of the 5 bands they took was with the H alpha, the narrowband H alpha.
Sure.
So we actually already have, so that is slightly better resolution, the Hubble, than the Webb at that wavelength.
Oh, okay.
Simply because we're slightly slightly oversampling the H alpha. Is that right? We're not at Nyquist sampling. We're not at the ideal sampling. Okay. And there's no need to have taken that. So yeah.
Okay.
And the cool thing is, so combining the H alpha with the Passion alpha, the 187 channel, not only can we see, we can reinforce our idea of where those hydrogen clumps are, but if we compare the relative strengths of the hydrogen alpha versus the Passion alpha, we can actually see exactly how much dust extinction there is, which tells us a lot more about the galactic environment there too.
Wow. Yeah, an embarrassment of riches.
It is, yes.
Well, I guess we're done. Any final comments, Patty? Do you have anything to say?
Just, I hope my brother feels better really, really soon.
Yeah, get well, Michael.
Let's send healing thoughts to.
And you're not going to be there tomorrow, are you?
It's outside, so probably.
Oh, okay. Mask
All right.
up.
Just wear a mask.
Yeah, I have one final question, if I might. Yeah, so you're able to use the recombination lines, hydrogen recombination lines, to work out extinction. Yeah. So the thing is, when you see it in mission, you could work out maybe dust column density. So can you make a sort of a rough estimate of how deeply embedded the sources are in the dust? I mean, how
yes,
and that's along the line of sight.
Yep, and that's precisely one of the things. So with the Passion alpha wavelength, so the 656.3, that's the 3 to 2, and the Passion alpha is the 4 to 3 transitions. Quantum mechanically, we expect that the H alpha line should be about 4.5 to 5 times stronger than the Passion alpha. So that's our prediction. That it's about 4 to 5 times more likely to go from the 3 to 2 than from the 4 to 3. So we have our baseline. If there's no dust at all, that's the relative strength. What we see though often, and this is one of the things that I'm literally hoping to do here in the next week or so, I want to make a map of what the multiple from the H alpha compared with the Passion alpha is, because the higher up we go, if it's, for example, the H alpha is 12 times stronger than the Passion alpha, we know that's a direct measurement of that column density there. So yeah, that's exactly one of the things we are looking at.
Okay. Thanks.
All right.
Cool.
Well, let's call it a close. And Tony, we all look forward to you coming back and telling us what's what.
Anytime. And then thank you all very much for listening. So
All right.
Thanks, Tony. It was
Thanks,
interesting.
Bill.
Thank
Bye,
you. Go
Tony.
well.
Bye.
As always,
Bye-bye.
all right. Be safe.
everybody.